Hi again, and welcome to Chapter 2, Section 2. And today we're going to talk about limits and continuity. So I think we've hinted around at limits, but let's talk about what limits actually are. The limit of a function describes the behavior of the function when the variable is near but not equal to a specific number. If the values of f of x get closer and closer, as close as we want to one number, L, as we take values of x very close to but not equal to a number, C, then, so let me explain this before I read the rest. Basically, if you look here, it says the limit describes the behavior of a function when the variable is near but not equal to a specific number. So if we follow this graph from this way and from this way, they're both heading to the same place, right? We can say for this function that the limit of f of x as x approaches C, because we're getting closer and closer to C, but we don't have to be equal to C. So that's going to equal my L value. Okay. So now we have f of C. Well, f of C doesn't exist. It's undefined, right? So this is undefined because this is not the limit. This is just f of C. We can see there's an open circle there. So f of C doesn't exist, right? Then we have the limit as x approaches C of f of x. That's different. So if we want to know what the limit as x approaches C is, basically it says underneath here, describes the behavior of f of x near, but not at the point x equals C. Basically, what we're talking about is, as I get closer and closer to C, from both sides of this graph, I can tell that my value gets closer and closer to L. So we have this limit. So here, when it says the limit as x approaches C of f of x, it's equal to L. Because all we're looking is for the behavior of f of x near, not at the point x equals C. So like we can say that point here, let me make a point. We can say this point here is pretty close to C, but it doesn't equal C. But as we get closer to where that open circle is, what's happening with my y values is they're getting closer and closer to L, the limit. Okay, so this is really important. Near, but not at. Okay, so if we have a graph, it's usually easy to determine the limit because you can see it. Okay, so let's do this first example. The limit of f of x as x approaches 1. So I look and I say, okay, it's coming into 1. At 1, it looks like it's 2 from both places because 1, we have a point, and it's 2. So this would equal 2. Now, let's look at f of 1. Well, f of 1 is really like saying what's y when x equals 1. So I come here, there's a point there. So f of 1 also equals 2. Okay? Let's look at 2. So at 2, we're saying the limit as x approaches 2 from both sides here, and that's equal to 3. So this equals 3. But if I look, f of 2, well, f of 2 doesn't exist, right? It's undefined. Okay? Okay, let's talk about 3. So the limit as x approaches 3 of f of x. So, okay, that's approaching 3. That's approaching 3. They're both getting closer to the same number, which is 1. So here I can say this equals 1. But if we just look to see what f of 3 is, f of 3 is this closed point right here, which equals 2. Okay? Because the actual point is at 3, 2. Now let's look at 4. F of 4, well, if I come in from this side, I get to here. And if I come in from this side, I get to there. They're not going to the same point, are they? That means we would say this limit does not exist. And sometimes we abbreviate it DNE. Okay? But f of 4, there's a point there, isn't there? When I get to 4, f of 4 is actually equal to 1. So I hope that was clear. We can also explore limits using tables and algebra. So this right here is a table. I just left it because it would take us just a long time to fill this in. But basically, we're looking at if you have this function here, and it says approaching 1. So we want to get x closer and closer to 1. So we start at 0.9, and then we get 0.998. That's closer to 1. This is closer to 1. This is closer to 1. And there's my x. They're not equal to anything, but x is getting closer and closer to 1. As x gets closer and closer to 1, what happens to y? It gets closer and closer to 3. This is what I'm doing here is if I have a graph, and this is 1, I'm coming in from the left side here, and I get certain y values. This other graph is getting closer and closer to 1 from the right, isn't it? So if I plug in all my numbers, notice this is 1.1, this is closer to 1, this is closer to 1, closer to 1. Basically, as x gets closer and closer to 1 from the right-hand side, we have the same limit. Okay? So we can say here, the limit equals 3. There are some tables that you can make that could trick you, but in general, we could do this. Okay? Now we can use algebra. This is the same function. 2x squared minus x minus 1 for x minus 1. So if we want to use algebra, the first step has to be we have to factor. Factoring tells us whether or not we have an asymptote or a whole. Okay? We have an asymptote if after we factor and simplify, and we still have something in the denominator, we have a vertical asymptote. But if everything cancels, we have what we call a whole. And I'll try to describe it. So let's factor the numerator. You get 2x times x, and then 1 and 1, and then outer and inner. So outer would be 2x, inner would be 1x. Since we want it to be to be negative, this would have to be negative. This would have to be positive. Then I'm going to divide that by x minus 1. Factored my function, notice this cancels with this. And what do I have left? I have a line, 2x plus 1. That's it. So what we can do here, so first step, second step, cancel like factors. If the function can then be evaluated, we have a whole. So like what that means is now really this is saying the limit as x approaches 1 of 2x plus 1. Because remember, we're looking at the limit, so the actual value isn't, we're not using 1. If we were, we would get 0 over 0. So we're saying, okay, we're going to make 1, just take it out. We can't use 1, so we'll make a whole in the function when x equals 1, which is what you see right here. Once we do that, I just have 2x plus 1, which is a line. And I can find every value for x except when x equals 1, because x is a whole. I hope that makes sense. If not, you're welcome to come ask me questions. I'd love to have you show up in my office hours. It would be, I'd be happy to help you with anything. All right, so I plug in 1 now. I get 2 times 1 plus 1, which equals 3. That agrees with our table and our algebra. Okay, so now we're going to just talk about one-sided limits. And we've kind of seen one-sided limits. I've drawn one-sided limits, but I didn't explain one-sided limits. So let's say I have a function that looks like this. And there's a hole here. And let's make it a closed circle here. And it goes out this way forever and this way forever. Okay? So we have what's called the left limit, which means I have this function, and if we call this value right here c, the limit as x approaches c from the left, or you could say, because there's a negative there, you could say from the negative side, because it is actually coming in from a negative infinity. And we can see that we get to this point right here. And let's just, for the heck of it, okay, we can call this L1. We have the limit of f of x as x approaches c from the left, and we can see that equals L1, right? But I can also have a right-hand limit. A right-hand limit means I'm starting right of the value that I'm looking for, and I'm coming in towards the C value. And notice I have another value there. We can call this L2. This is the picture of a right-hand limit or a left-hand limit. It just depends on what you're looking for. The only way that the limit of this function as x approaches c exists if the limit as x approaches c from the left is equal to the limit as x approaches c from the right. So this with no plus or minus only exists if it goes to the same value from both sides. This is another example, and we're going to evaluate one-sided limits of this function. So basically, they're telling us x equals 0 and x equals 1. So I want to say the limit as x approaches 0 from the left. And this is f of x. We want to find the limit as x approaches 0 from the right. So that takes care of 0. Then we want the limit of f of x as x approaches 1 from the left, and the limit of f of x as x approaches 1 from the right. Okay? Easy. So let's go to 0. Here's 0. If I approach, this is x equals 0. Okay? So if I get closer and closer, here I'll use a different color. So as I get closer and closer to 0 from the left, I can say this equals 1. As I get closer and closer to 0 from the right, well, that's 2. So since the limit from the left is not equal the limit from the right, the limit as x approaches 0 of f of x does not exist. Okay, because they're not the same. Let's look at 1. So as I approach 1 from the left, I'm coming in toward y equals 1. So y equals 1. If I come from the right, we come to the same place. Y equals 1. Since they're equal, we can say the limit as x approaches 1 of this function is equal to 1, because it's from both the left and the right, it's coming to that point where y equals 1. All right, now we're going to talk about continuity. So a function that is friendly and doesn't have any breaks or jumps in it is called continuous. More formally, luckily, because friendly is not an easy word to break down mathematically. So more formally, the definition of continuity at a point. A function f is continuous at x equals a if and only if the limit of f of x is equal to f of a. Okay, we'll see how that works. Another way we could do it is we can have like 3 statements. So we could have one statement that says, what's f of a? We can have another statement that says, what's the limit as x approaches a of f of x? And then third, we can say, If these two are equal, then if all three things exist and are true, then we have continuity. So this is a real brief description of these three steps. Okay, so let's look. Behaviors at x equals 2 and x equals 4 exhibit a hole. This hole, so the holes they're talking about are this hole and this hole. So those are two holes. Those are called removable discontinuities, because if I defined the function at x equals 2 to be 2 for both of them, I would fill in the holes and they would have continuity there. Both of these graphs at these points when x equals 2 and when x equals 4 would be continuous if I filled them in with a point. So we can remove the discontinuity if we wanted to. Okay? However, the behavior at 3, so here at 3, this is called a jump discontinuity. We can't do anything to make that come together. There's nothing we can do. It's just discontinuous there. So a way to know if something is continuous, this is the formal way to know if something is continuous. But if you can draw a graph without picking up your pencil, it's continuous. If you have to pick it up because there's a hole, or because there's a jump discontinuity, or there's an asymptote, or some reason that you cannot get to that point, the graph is not continuous at that point. Okay? So if we were to look at this, let's answer these questions. So f of 1, here I'll highlight them. So f of 1, we go x equals 1, f of 1 is equal to 2. Easy. F of 2, oh, there it is right there, isn't it? It's equal to 1. F of 3, here's my point, so it's equal to 2. F of 4, well, there is no f of 4. It's undefined there, right? Like this is f of 4. There's no closed circles. There's no point there. This is undefined. Now let's look at the limits, because the limits are different. They don't have to exist at that point, just near it. This is A. So we're saying when x gets closer and closer to 1. So here we're getting closer to 1 from the left. Here we're getting closer to 1 from the right. And both of them get closer and closer to 2. So our limit here is also 2. When we do 2, so here's 2, my value gets closer and closer here to 2, and closer here to 2. So my limit here is equal to 2. Let's do 3. So when x is 3, my limit here goes to 2, and my limit here goes to 1. This we call does not exist. We don't have a limit there. We can't say it's anything because as it comes from the right and it comes from the left, they're two different values, no limit. And then for 4, from the left, from the right, they both come closer and closer to that point. That point is 2. So I actually have a limit here of 2, even though it's undefined at that point. So they are different because these are equal. This is continuous. If we go through the 3 steps I wrote, so f of a exists. They both have to exist. I guess I should put that there. So let's say f of a exists. Yep, 2. The limit of f of x as x approaches a, 2. Good. If the limits are equal, it's continuous. There we have it. It is. Now, for 2 here, this is really a equals 2. Okay? So when a equals, so we're on the second one. Okay. So when a equals 2, so we're here. We don't have to look at the graph. When a equals 2, I have f of 2 is equal to 1. I have the limit exists, but notice the limit is not equal to f of a. I know for sure here it is not continuous. Okay? Next, a equals 3. So I have f of a exists? Yeah, 2. The limit exists? No, does not exist. Not continuous. And for the last one, well, we already said it's undefined, so it's not continuous here as well. Okay, look at the graph. Well, at 1, so if I was going to draw this graph without lifting my pencil or pen, well, let's see how far I get. Uh-oh, what do I do here? Because really, I need to kind of come down there, but I have to come back up. I guess I could have done it without lifting it, but not really, because I would have had to lift it and then continue along here. There's no way I can get from there to here. So I have to lift it here and then lift it again. So if I say L is lift, I have to lift my pencil here. I have to lift my pencil here. And I have to lift my pencil here. So it is not continuous at those points. And we proved it by showing those 3 things, which is really the same as this. A function is continuous at x equals a if they're only giving you the last one, but you have to calculate the other 2 before you get to the last one. So basically, my 3 steps are the same, whichever you like better. And let's see, we have, so which functions are continuous? It turns out pretty much every function you've studied is continuous where it is defined. This is important. It's not saying it's continuous where it is defined. So we've looked at polynomials. Actually, polynomials are always continuous. There's nothing to make them not continuous. They don't have no denominators, nothing. Radicals are like square roots, are continuous everywhere they're defined. If it's a square root, it's only defined from 0 to infinity, but it's continuous there. Rational, as long as, so rational numbers are polynomials over polynomials. We have to be careful here. Here, if denominator does not equal 0. But again, they've handled that by saying where it is defined. So it's not defined there, it's not continuous there. And then we also have exponential and logarithmic. They're continuous everywhere they're defined. They're just not defined everywhere. Okay? So moreover, any combination of continuous functions is also continuous. Meaning if I add two functions that are continuous, they'll still be continuous, and so on. So this is helpful because of continuity says that for a continuous function, since the limit of the function as x approaches a has to equal f of a, that means for a continuous function, we can find the limit by direct substitution, which is the same as evaluate the function, if the function is continuous at a. So how would you tell? Well, first thing let's do is let's plug in a value and see if we get a value. So if we plug in 2 here, we would have 2 to the third power minus 4 times 2. This is equal to 8 minus 8, which is 0. So at x equals 2, this is defined. It's continuous. I plugged it in. So I know f of a exists, which is f of 2. And I know because there's nothing here stopping it. I don't have any holes. I don't have any jumps. I know that this is going to be continuous. Let's prove continuity using our three steps. So f of 2, well, it exists. I plugged it in, it exists. The limit exists. When I plug it in, I get the same number. And they both equal 0. F of 2 equals 0. When I plug in 2, I get 0. And the limit as x approaches 2 equals 0. So I can say the limit of f of x as x approaches 2 is equal to f of 2, which means this function is continuous. Okay? Let's do the next one. So let's plug in 2. So I plug in 2. Basically, I'm saying number 1, f of 2, and my function is x minus 4 over x plus 3. Plug it in, I get 2 minus 4 divided by 2 plus 3, which is equal to negative 2/5. Well, that exists. Number 2. Well, again, the limit exists. If I plug in 2, I get the same thing. So the limit as x approaches 2 of x minus 4 over x plus 3, plug in the numbers the same, I get the same minus 2/3. So yes, the limit as x approaches 2 of x minus 4 over x plus 3 is equal to f of 2. So what can I say? I can say this is continuous. It's continuous at x equals 2. It may not be continuous somewhere else. What we really should test for is x equals negative 3, because that's probably a point of discontinuity. Last step. So here, number 1, f of 2, I plug it into my function, I get 2 minus 4 over 2 minus 2, which equals negative 2 over 0, which it's not defined, it doesn't exist. So right here, we can stop As long as one doesn't work, you're done. So this is not continuous. As soon as any of these fail, the whole thing fails. It's not continuous. And that's pretty much it. That's 2.2. Thank you very much. See you for 2.3.